The goal of this project is to improve the ability of a robotic stand-up comedian to adapt to audience responses during a performance, allowing it to behave more like a human performer. This will improve the interpersonal communication between the robot and its audience. The implications of this work can be applied in multiple areas as human-robot interactions become more common and need to feel natural to engage in, such as using AI personal assistants. After the robot tells a joke, it listens to how the audience responds. If it hears that the joke received near unanimous approval, it can add an extra remark before moving on to the next joke, acknowledging their positive response. If it determines that the joke was poorly received, it can make a self-deprecating remark or other appropriate acknowledgement before moving on. The main task for our team was to develop a reliable method the robot can use to make this determination of whether a joke was well received or poorly received. First, a script is used on the original recording from the comedy performance to split it from one file into multiple short MP3 files. The resulting joke files contain the audio of the robot telling the joke. The pause files contain any audience response that was detected from the time the joke stops being spoken until the next joke begins being told. A tool called Pratt is then used on the audio files to extract whatever features we want to be able to use in our analysis, for example, pitch and intensity. A human then listens to the audio for laughter, and based on what they hear, they assign that joke a rating.
We identified 3 possible audience responses, a positive, neutral, or negative response. We then took the mean of the 3 ratings, rounded to the nearest integer, and used this as our ground truth rating. The next step was to create a reasonable goal for the accuracy of our classifier. In order to obtain this, we compared each group member's ratings to the ground truth in order to get their individual accuracy. What we found was that there was a mean of about 80% and a median of about 83% accuracy. Since our goal was to create a classifier with an accuracy rating comparable to that of humans, we believe that these results justified our initial goal of having 85% accuracy on the classifier. The features we selected to extract from the audio were the mean and standard deviation of the pitch, the mean and standard deviation of the intensity, and the minimum and maximum amplitude. The next step was to do a cursory analysis of our data. So as you can see by this scatter plot, which shows the 3 audience responses relative to intensity and intensity standard deviation, even with only 2 features, we have a strong degree of separability between our negative, neutral, and positive audience responses. The next thing we did was to implement some basic classifiers. We started out with 4 simple classifiers: the support vector machine, decision tree, k-nearest neighbor, and neural network. And we used 2 different validation techniques: leave one performance out and holding out 20% of the data. And this graph shows the results of our initial classifiers. As you can see, our support vector machine tended to be a little under 70% accurate. Our decision tree was around 75% accuracy. K-nearest neighbor a little under 75, and neural network also a little under 75%. So the next step was to introduce normalization and parameter tuning. We tested 2 different types of normalization to begin with: min-max normalization and standardization. And then we used log10 parameter tuning to avoid overfitting. And we found that this improved accuracy by about 5 to 10% per classifier. So as you can see in this graph, which shows the movement from the original classifier to normalization, we had about a 5 to 10% accuracy improvement for each one. From here, we were able to make further optimizations and add more features in order to improve the analysis of our data. All of the classifiers are over 80% accurate, with our support vector machine, naive Bayes, and random forest classifiers all being over 85%. And this shows the decision boundary for our naive Bayes classifier. It's our second most accurate classifier at about 86%. And this slide shows our most accurate classifier at the moment. This is our radial bias function support vector machine. It has about 88% accuracy compared to the ground truth. And that concludes the section on the post-joke classifiers.
Our project started with just post-joke laughter detection and rating, but our client also wanted us to expand on this idea by implementing a mid-joke laughter detection. We decided to do something similar to the post-joke analyzation, but switch to a different rating system, from a 3-point rating to a 2-point rating, which is just good and bad. So in this graph here, we see that pitch and standard pitch that has a high correlation value, close to 1, which exactly is 0.875. And in this next graph, we see that the correlation between intensity and max intensity is very low. If the correlation is highly related between two different features, we could remove one of the two features, since two highly correlated features may not be helpful to classify data into two groups, since they may contain repetitive information.
So you can see the graph here, we have a two category. One is class A, the other category is class B. And X1 here represent the feature, and X2 represent another feature. So let's say we want to identify this red star. So we're gonna select the three nearest neighbor. So three nearest neighbor, we have a 2 purple and 1 yellow. Then we're gonna classify this red point belong to class B because there's 2 purple point and there's only 1 yellow point. And eventually we got our average accuracy is actually 68%. And the second model we use is decision tree. Basically, in each node, we're gonna come up a question to separate the data into two groups. The first question we ask is the maximum pitch smaller than 263? So that's how we separate data and make so many different categories to split our data into two groups.